Ever wonder how a database can be lightning fast, doing all its work in memory, but at the same time promise you that if the power cord gets kicked out, not a single bit of your committed data is lost? Well, the answer is this really elegant, really powerful idea at the heart of pretty much every database you've ever used, the write-ahead log. So today, let's pull back the curtain and see how this thing actually works.
All right, here's our game plan. We're going to start with the fundamental problem that every database is trying to solve. Then we'll introduce the write-ahead log, the WAL, as the hero of our story. We'll dig into its core rules, the performance trick that makes it all practical, and finally, we'll look at a really subtle problem that needs one more layer of protection to make things truly bulletproof.
So, first things first, we have to understand this core tension, this fundamental conflict that sits right at the heart of every single database system. The tug-of-war between going fast and being safe.
Here's the deal. To be fast, databases absolutely have to use memory, a buffer pool to cache data. It's just way, way faster than going to disk every time. But as we all know, RAM is volatile. The server crashes, the power goes out, and poof, everything that was only in memory is just gone. This is all about the D in ACID, durability, and it is completely non-negotiable. So how do you get the speed of memory and the safety of disk?
I mean, look at this. This is the nightmare scenario, right? It's so simple and so dangerous. An update happens in memory, we turn around and tell the user, yep, all good, your data is saved, and then, boom, the power goes out. The user thinks their critical information is safe, but it actually vanished into thin air. That's not just a bug, that is catastrophic data loss.
So the most obvious solution, you might think, is what's called a force policy. Just write every changed piece of data straight to the disk right away. The problem? That is a performance disaster. You're doing slow, random disk writes for every tiny change, and that completely negates the entire reason you have a fast in-memory buffer pool in the first place. What we want is the holy grail, a no-force policy, where we don't have to wait for the disk, but somehow, magically, it's still perfectly safe. And that magic, that brilliant idea, is the write-ahead lock. This is the mechanism that lets us decouple performance from durability. It lets us separate the act of making a change safe from the slow, expensive act of actually writing the data page to its final place. The whole thing hinges on this one simple, unbreakable promise. Before you're even allowed to think about writing your modified data page to the main data file on disk, you first have to write a little note to yourself somewhere else, a note that's durable, describing exactly what you're about to do. That little note, that's our log record.
And this is exactly why it's so fast. Think about it. Writing big 8-kilobyte data pages means jumping all over the disk to find the right spot. That's slow, random I/O. But writing a tiny log record, that's just adding a few bytes to the very end of a single file. It's a purely sequential write, which is orders of magnitude faster on any storage you can think of, from old-school spinning Rust to the fastest NVMe drives.
Okay, let's run that crash simulation again, but this time with the WAL. The update happens in memory, but now, before we tell the application success, we write a small log record to our special log file, and we make absolutely sure it's physically on the disk. Now when the crash happens, it doesn't even matter that the in-memory data page was lost. When the server boots back up, the first thing it does is read the log, see the change that was about to happen, and it just replays it. Simple as that. Your data is safe. So now that we see the basic idea, we need to get into the really strict rules that make this whole system foolproof. It's not just a good idea, it's a protocol with laws that cannot be broken.
The very first rule is all about time. Every single record that gets written to the log gets a unique, always increasing ID number. We call it the log sequence number, or LSN. You can think of this LSN as the master clock for the entire database. It creates a perfect, linear, unambiguous history of every single modification that has ever occurred.
And that master clock lets us enforce the absolute most important law of the WAL. See, every data page in memory keeps track of the LSN of the last change made to it. We'll call it the page LSN. The rule is dead simple. You are forbidden, absolutely forbidden, from writing that page to disk if its page LSN is newer than what has been safely saved in the log file. In other words, the log must always be ahead of the data files. Always. Okay, so what information do we actually put inside these log records? Well, there are a few different ways to do it.
You could do physical logging, just the raw byte changes. It's simple, but it can be really verbose and fragile. Or you could do logical logging, just recording the SQL statement. That's super compact, but recovery can be slow and complicated. The sweet spot, the Goldilocks solution that most modern databases use, is called physiological logging. It records physical changes, but within the logical context of a page. It gives you the best of both worlds. It's fast, it's robust, and it's pretty darn compact.
This all sounds fantastic, but there is one little performance catch that we haven't talked about yet, and that brings us to group commit. This is the optimization that lets the whole system absolutely fly when it's under heavy load.
So here's the bottleneck. It's a system called fsync. This is how our program tells the operating system, hey, I'm serious. Stop what you're doing and make absolutely certain this data is on the physical disk right now. And even for our super fast sequential log, that call takes time, maybe around a millisecond. Now, a millisecond doesn't sound like much, but if you want to do thousands of transactions per second, you can't afford to wait a millisecond for every single one. You'd top out at 1,000 TPS, period.
And the solution is just brilliant. It's called group commit. Instead of every transaction making its own expensive fsync call, they all just add their log records to a shared buffer and then they wait. Then, a separate, dedicated Flusher thread wakes up every few milliseconds, grabs that whole batch of log records from all those waiting transactions, and writes them all to disk with a single fsync call. Once that's done, it wakes everybody up and tells them, okay, you're all safe now. We just paid the 1 millisecond tax once for dozens or even hundreds of transactions.
And the result is, well, it's dramatic. This isn't just a minor tweak, it's a total game changer. By batching these FiSync calls, you can blow past that 1,000 TPS limit. Your throughput can go up by orders of magnitude. This is what makes a truly high-performance, safe database possible.
We are so close. We have this robust, incredibly fast system. But there is one last, really subtle vulnerability that the write-ahead log by itself doesn't solve. This is that last little piece of the puzzle, the problem of torn pages. A torn page is exactly what it sounds like. Imagine this. We followed all the wall rules, our log is safe on disk, and now we decide it's time to write our 8 kilobyte data page to the main data file. What happens if the power dies after we've only written the first 4 kilobytes? The page on disk is now garbage. It's half old data, half new data. It's literally torn in half and it's completely corrupted.
And this is the critical failure mode. The crash happens during the data page write itself. A checksum will definitely tell us that the page is broken during recovery, but the WL can't help us here. The WL needs a valid page to start with before it can apply its logged changes. If the page itself is unreadable garbage, we're stuck.
So how do we fix this? With what is essentially another smaller log, the double write buffer. The logic is simple. Before we do the risky operation of writing the page to its real location, we first write the entire page to a special, separate, contiguous area on disk and fsync it. Now we have a guaranteed, perfect, intact copy of the page tucked away safely. Then we can go ahead and try to write it to its final destination. If a crash happens and creates a torn page there, no problem. On recovery, the database just says, oh, this page is torn. Let me grab that perfect copy from the double write buffer, restores it, and then proceeds with the normal WAL recovery. Which brings us to a final, really interesting thought. We've gone to all this trouble to protect our main data files, right? The wall, the double write buffer. But if you stop and think about it, if the write-ahead log contains a perfect, ordered, complete history of every single change ever made to the database, what are the data files really? They're just a cache, a big, convenient performance optimization of the one true source of truth. And that source of truth has always been the log.